So we've looked previously at inertia and how it's incorporated into Newton's first law of motion by looking at the inertia of objects both moving and at rest. Now we're going to focus on the inertia of just moving objects. When we combine the concepts of inertia and motion, we are dealing with momentum, which is a word we've all likely heard before and probably have a good idea of what it is. However, we're also going to focus on something called impulse, which is probably a term you're not too familiar with. By the end of this video, we should have a good understanding of momentum and impulse, be able to do some simple calculations of each, and also be able to describe ways to reduce the force on an object in a collision. So momentum is a word we've all heard before and probably have a good idea of what it is. We can all likely identify that a truck moving at 30 miles per hour has more momentum than an identical truck moving at 15 miles per hour. What might be a little bit more difficult to identify is the fact that an aircraft carrier moving at 2 miles an hour has way more momentum than our truck carrier, even if it's moving at 100 miles an hour. That's because momentum is dependent upon both mass and velocity. In physics, momentum is defined as the product of mass and velocity. We represent momentum by the symbol P, and it's measured in units called a kilogram meter per second. Okay? The equation for momentum is mass times velocity. So the faster an object moves, the more momentum that it has. Similarly, the more mass an object has, the more momentum it has. That's why a slow-moving aircraft carrier has so much more momentum than a speeding truck. So now let's go ahead and look at impulse. So to discuss impulse, we're going to use this example of pushing a crate across a floor. It's a simple example, so it's going to be easy to visualize this new concept of impulse. From the equation for momentum, we can see that if the momentum of an object changes, then either the mass or the velocity or both change. Now, in our everyday experience of moving objects, we rarely see an object's mass change during a motion. It's much more likely to see the velocity change and the mass remain constant. So we're going to set the condition in our example here that the mass of this crate does not change, but we want to change its momentum. So how can we do that? What do we need to do to the crate to change its momentum? Well, clearly, one thing we can do is change its velocity. If the velocity is changing, that means there's an acceleration, right? Well, after all, the definition of acceleration is changing velocity. So, what produces that acceleration? Well, we know from Newton's laws that the answer is a force. So, the greater the force acting on an object, the greater its change in velocity, and therefore, the greater its change in momentum. So, I can change this crate's momentum simply by pushing harder on it, right? If I increase the force acting on the object, I'll be able to increase the momentum. But what if I push so that the crate's velocity does not change? I push it with a constant velocity instead. Is there another way to change its momentum? Well, if I push for a longer amount of time, I can change its momentum a greater amount. So a force that's sustained for a long time produces more change in momentum than does a force that is applied for less time. So both force and time interval are important in changing momentum. The quantity, force times time, we refer to as impulse. So when we're talking about impulse, we're talking about a force acting over times a time interval. So an impulse delivered to an object will produce a change in that object's momentum. So we say that impulse is equal to the change in momentum. We already know that we can symbolize change by using a delta in front of whatever we are changing. We can use that triangle delta symbol. So we can rewrite this relationship as this right here. This is called the impulse momentum theorem, and it helps us to analyze many examples where forces act and momentum changes. Sometimes the impulse can be considered to be the cause of a change of momentum. Sometimes a change of momentum can be considered to be the cause of an impulse. It doesn't matter which way we think about it. The important thing is that impulse and change in momentum are always linked. So now we want to look at some ordinary examples in which impulse is related to increasing momentum, to decreasing momentum over a long time, and decreasing momentum over a short amount of time. So first, we want to talk about increasing momentum. So in order to increase the momentum of an object, we have to apply the largest possible force on that object for as long as possible. So take hitting a golf ball, for example. When the club hits the ball, the force that's exerted is not a constant force. That force increases to a maximum as the club strikes the ball and then decreases as the ball moves away from the club. We can see an example of this, another example of this in kicking this soccer ball. So as the foot begins to come into contact with the soccer ball, the ball deforms until that force is at a maximum, and then that force lowers back to zero as the ball moves away from the foot. So the force of a kick or a hit on our golf ball is going to go up and then come back down. So there's our force, and here's time. Now, if you were to stop the club midway through striking the ball, right, so like right in this area there, then you would not end up changing the ball's momentum as much as you'd like, and it wouldn't go as far. So to fix this, you need to make sure that the club is in contact with the ball as long as possible. This is why when you're golfing, you need to, they say, to follow through with your swing. So you get that following through makes sure that that club head is in contact with the ball as long as possible. The same is true like when you're playing pool, you follow through on your hit, or you're playing basketball, you follow through with your shot. You're playing baseball, you swing at the ball, you hit the ball, you got to follow through with the bat, whatever. If you're hitting something, following through allows that average force with which you're hitting that thing to act for the longest amount of time, thereby changing its momentum the greatest possible amount. So we can also talk about decreasing momentum over a long period of time. Let's imagine you're driving your car down a hill and suddenly the brakes go out. So you can't stop. At the bottom of the hill, you see a large boulder and a large stack of hay. The stack of hay is clearly large enough to stop your car, okay? So which would you rather run your car into? The boulder or the stack of hay? Well, obviously the stack of hay, right? But why? Well, to bring your car from its current speed to a stop will require a change in momentum. Now, whether you run into the boulder or run into the haystack, the change in momentum is going to be the same for each. This change in momentum is brought about by delivering an impulse, and this impulse will be the same for each case. So the impulse is going to be the same for each of these two ways to stop your speeding out of control car. Okay? But what's different is going to be the amount of time that it takes to change that momentum. So the time over which that impulse acts is different for these two cases. The boulder will change the momentum over a very short time interval, while the hay will change the momentum over a much, much longer time interval. So by looking at this impulse momentum theorem, where we know that however long it takes to stop the speedaway car, right, the change in momentum is going to be the same for either case, haystack or boulder. Also, the impulse delivered will be the same whether you run into the haystack or the boulder. What's different is the time interval. The boulder will be a much shorter time interval. So the effect of that is a much greater force using the boulder to stop. Okay, so it's a much greater force. Here, with the haystack, you'll have much less force to stop the car. It's because of this that things like padded baseball gloves and car airbags work. They each increase the amount of collision time thereby reducing the amount of force experienced. So we can also talk about decreasing the momentum over a short period of time. So imagine you're playing a water balloon toss game where you toss a water balloon back and forth while stepping backward one step after each successful throw. Eventually, you and your partner are far apart and your chances of success become much lower. They become much lower because the water balloon is traveling faster by the time it reaches you, so it has a greater momentum. One way to improve your chances of not breaking the water balloon when you catch it is to kind of go with the water balloon as you catch it. You move your hands away from the water balloon as you catch it. In order for an object to be brought to rest, the impulse that must be delivered is the same no matter how it's stopped. But if the time is short, the force will be large. Moving your hands backward as you try to catch the water balloon will increase the amount of time you're changing that balloon's momentum and result in less force being applied, and this fellow right here doesn't need to be quite so worried. Now finally, we want to talk about bouncing, okay? Let's imagine a flower pot falls from a shelf onto your head. That happens, you might be in trouble. But if it bounces from your head, you might be in a lot more serious trouble. Why? Because impulses are greater when an object bounces. The impulse required to bring an object to a stop and then throw it back is greater than the impulse required merely to bring the object to a stop. Suppose, for example, that you were to catch that flower pot with your hands. You provide an impulse to reduce its momentum to zero. If you throw the flower pot upwards again, you have to provide an additional impulse. This increased impulse is the same that your head supplies if the flower pot bounces from it. So, bouncing results in a greater impulse. So we're going to see examples of this and demonstrations of this and discuss more examples like this in class. So we'll see you then.